combination, series or parallel.
Parallel?
Those two are in parallel. We'll see, if it's not clear, I'll see in a moment why. And this one is in series with these two, right? So now what we're going to do is we say we're going to reduce the circuit. We're going to simplify it. So here is how it gets reduced. So you write double arrow like this. Here is my battery. Here is C1 equals to 3 microfarads. I didn't do anything yet, right? This is the battery, so it's 12 volts, same battery. Now these two that are in parallel, I'm going to replace them by C equivalent, C23. And the question is, what is C23? These two here, if I were to replace them by one capacitor, what would it be? Since they're in parallel, what can we conclude?
They're the sum of.
The sum, right? Yeah, you just add the two capacitances. So in parallel, C equivalent just adds the the capacitance. I don't have three capacitors in parallel here, we just have two, and they're called 2 and 3. So we add them. So what's the total capacitance of capacitors 2 and 3? 6. 6, yeah. So there's 6 microfarads. And now I'm going to finally have just one capacitor. Now, here is the battery. Now, this one here is C1, 2, 3. All the capacitors, basically. That one capacitor is equivalent to all these here. To all these. So, what would that capacitor's capacitance be? Well, it's a combination of these two. These two are in what?
Series.
They're in series. So, how do capacitances add in series?
1 over 4.
Yeah, you add the reciprocals and then do 1 over, right? So, for this one here, you would have this. You would have 1 over C1, 2, 3 is equal to 1 over something plus 1 over something. What are those somethings?
C1 and C2, 3.
This one, right? This one. 1 over this one plus 1 over this one. Okay, so it's 1 over 3 plus 1 over 6. By the way, you don't have to convert to farads at the moment, because you can change, but then at the end you will have something times 10 to the minus 6, which will be in microfarads anyway. So I will leave it in microfarads, and the result will be also in microfarads. So now, what is 1 over 3 plus 1 over 6? So 1 over 3 is 2 over 6. So you get 3 over 6, which is 1/2, right? So this is 1/2. But that's not C equivalent. 1 over it will be C equivalent. So C1, 2, 3, or C equivalent, if you like to name it that way, which is equal to 2 microfarads, right? 2 microfarads. Yeah. Well, I haven't solved the problem they gave me, but we're getting there. So now, why is this useful? Well, C1, 2, 3 is the equivalent to these two that are in series, right? So if I find the charge on C1, 2, 3, it will be the same as the charge here, and it's the same as the charge here, because they're in series, and the charge in series is the same. So let's find the charge on C1, 2, 3. We will call it, I guess, Q1, 2, 3. Okay, so let's find the charge on the C1, 2, 3. So Q1, 2, 3 will equal to the voltage of the battery, right? Times C1, 2, 3. What's the voltage of the battery?
12.
12, yeah. And then C1, 2, 3 is 2, right? Microfarads. So 2 times 10 to the minus 6 farads. And that means Q1, 2, 3 is equal to 24 times 10 to the minus 6 coulombs, which is 24 microcoulombs. Okay? 24 microcoulombs. So that means, what's Q1? What's the charge in capacitor 1? Also 20. Yeah, 24. Because they're in series, and the equivalent capacitance in series has the same charge. So that means Q1 is equal to 24 microcoulombs. Let's find the voltage across capacitor 1. So what's the voltage on a capacitor? How is it related to its charge?
Charge times capacitance.
Yeah, so we know that voltage V1 will be charge 1 over what? Capacitance 1, right? Yep. Till I lost some. Or is that just obvious? This stuff kind of tedious? Okay, I know a lot of you probably did it in high school or something. If it's clear, I would just no?
It's processing.
Okay, alright. So you got Q1 is the 24, right? Microcoulombs.
Yeah.
And C1 is 3 microfarads.
Yeah.
So when you divide micro by micro, micro goes away.
Yeah.
So you will have 24 over 3, which is what?
8.
8 volts. Let's write it here. 24 times 10 to the minus 6. And this one is 3 times 10 to the minus 6. And it turns out to be 8 volts. Okay. 8 volts, yeah. We did one piece. We found Q1 and V1. Q1 is what?
24 microfarads.
24 micro coulombs, and V1 is 8. Okay. So now let's go to Q2 and Q3. Now, what is the? Let's say I'm going around the circuit. You can take any path you like. As long as it's a closed path, then the change in voltage will be 0, right? The change in voltage will be 0. So let's see what I mean. Let's start here. What's the change in voltage from here to here?
12 battery. 12 volts.
12, yeah. And then, so you go here, and then what's the change in voltage from here to here? Now we know.
8 volts.
Yeah, it's 8 volts, but minus, right?
Right.
Because this side would be plus, right? We just found the voltage across capacitor 1, so this is 8 volts. So 12 minus 8, so how much is that?
4.
4. So from here to here, I must change by another, drop by another 4 in order to be 0 with that. Okay. Yeah, so, yeah, 8 plus 4 is 12. So the potential difference across this capacitor must be 4 volts. And the potential difference across this capacitor must be 4 volts. Alright, so, is that clear, or should I emphasize? So here's what I'm doing. The first one, I'm using this path. I'm starting here, and let's say I go around this way first, until I come back here. So I will increase by 12, and then drop by 8, because from here to here it's 8 volts, but I'm going the opposite way, so negative 8. And then I go this way from here to here, minus the voltage across capacitor 2, and then nothing until I get here, so I get 0. So that means V2 will be 4 volts. I can do this same path, or similar, from here to here, but I go this way. As long as it's a closed circuit, or a closed circle, closed path, I get 0. So, that will also give me V3 is equal to 4 volts. Okay. Another way to say it, C2 and C3 are in parallel, so they must have the same potential difference, same voltage. Long story short, V2 is 4 and V3 is 4. Okay? Now what are the charges on them? If you know the voltage, you know the charge. You know the voltage in capacitance, so you know the charge. So that means this. Q2 will equal to C2 V2. C2 V2. So C2 is 5, right? 5 microfarads. and then V2 is 4, so I get 20 microcoulombs, right? 20 microcoulombs. And then Q3 will be C3, V3, and so that's 5 micro, no, not 5, 1 microfarad, right? For C3, yeah, it's 1.
Oh, yeah.
And this one is 4, so you get 4 microcoulombs. What's the total charge on Q2 and Q3? 24. And they're in series with this one, which has 24, and it should be 24.
Oh.
All right? Now that was that. In the worksheet, we still have a couple problems on these. So now, energy stored in a capacitor. So how much energy is there? How much energy does it take to charge it? And then once you charge it, your work is not wasted. When I say the battery's work is not wasted. So battery does work and then it charges the capacitor. So how much energy is stored in a capacitor? And you get that energy back when you discharge the capacitor. Okay, so how much energy does it have? So energy stored in the capacitor. So I know that voltage is a volt is a joule per coulomb, is the energy per charge, per unit of charge. So let's say if a potential difference is 12 volts, it means for me to take 1 coulomb from here to there, it costs me 12 joules, because it's 1 joule per coulomb. So if I'm charging a capacitor from no charge to some capital Q to some capital Q charge, then du, the small amount of energy I have to do, has to equal to, let's say the capacitor already has some voltage in it, some potential difference. So how much energy do I have to do to transfer another dq from the, so here's what I mean. So let's say I have some plus here and some minus here. And the question is, how much more energy does it take to take a plus from here and put it here? Another dq from here to here. Well, that amount of energy will be the voltage that you already have between the plates times the small amount of charge that you're trying to add on. That's the energy. All right, so now, but the voltage is equal to the charge that you already have on there divided by C. It's Q over C. So I would have dq, and then V is the charge that I already have divided by the capacitance of the capacitor, which is C. So U would be the integral from 0 to capital Q. I started with the capacitor uncharged all the way to its charging point. Capacitance is constant, so I'll put the 1 over C here. And here I have Q dq. Okay. When you integrate this, you get 1/2 of Q squared. Evaluate it from 0 to capital Q, so you get 1/2 of Q squared over C. So Q squared, here's the 1/2, here's the C. It's Q squared over 2C. Okay. Now you can replace Q by CV. So another form that you see is this. You have 3 quantities that you work with, Q and C and V, when it comes to a capacitor. So I can eliminate Q and just put the V and C. So Q is CV, so I would have C squared V squared if I replace Q. But I have a C on the bottom, so this would turn out to be 1/2 CV squared. That's another way to write it. And then another way, see, this one involves Q and C, this one involves C and V. How about Q and V? Well, you can eliminate Q by, eliminate C by saying it's equal to Q over V. So if you put Q over V here, 1 V cancels and you end up with 1/2 of Q times V. So all these are 3 forms that you see. The one I remember is this one. I always remember this one. It reminds me of like 1/2 mv squared. Yeah. Yeah. So, that's the energy when you charge a capacitor, yeah.
So U is like, or I guess du is the amount of energy you need to move dq.
A dq, yes.
Okay.
Yeah, it's a small amount of energy needed, yeah. And when you add all the du's together, you get the whole u. Okay, so, I mean, suppose you have a capacitor, suppose, just a quick example. If C is 220 microfarads and V is 330 volts. The voltage on the capacitor is 330 volts. The question is find U. It's a quick application of this, right? Which form would you use? This one or this one or this one? The middle one, right? Because you have these 2 quantities. You have V and C already. So you use that. So this one is like it says a camera flash capacitor. So they're trying to be practical. So we have a real life example. So the solution, U is 1/2 of C times V squared. We have 1/2 of 220 times 10 to the minus 6, right? Because it's microfarads. And then V squared is 330 to the power 2. And that energy turns out to be 12 joules. The author says, or gives an example to relate to 12 joules of energy. It's like if you have a weight 1 kilogram at about 1.2 meters, mgh is what? About 12 joules, mass times gravity times height. So if you drop that weight, 1 kilogram is like 2.2 pounds, it hurts.
Oh, wow.
It's so, yeah, it's a large charge, a large energy, especially if it gets discharged all at once. And you probably heard, like, if they say, if something is not plugged in, it doesn't mean it's safe to touch. Right?
So just charging.
And the reason is because you might have capacitors in there, they have charge, they're fully charged. And you touch them, and then they will discharge, and that discharge will go through you. And so, yeah, so you don't want, you have to be careful with capacitors. Yeah. Resistors and so on, they don't hold charge, but capacitors do. All right. Now the other one, the other important formula here is the energy stored in a field. And so I'm going to just or the energy density it's called. Okay. So energy density means you can think of the energy per unit of volume. How much energy you have per unit of volume. So here's what I mean. Energy density. If you have a capacitor, here is your capacitor. Let's say pluses here, and then you have the other plate, minus plate. So you have a field here, right? So the field exists within this volume, right? Between the 2 plates within that volume. And so this side here has area A, and the distance from here to here is D, right? D. So we know that, so let's define quantity U of E. It's the energy U over volume. It's the energy per unit of volume, joules per cubic meter. The joule per cubic meter. So let's see what it is. What did we say U was? We can write it as Q squared over 2C, or 1/2 CV squared, and so on, right? So I will use the middle one, 1/2 CV squared. So I have 1/2 CV squared over the volume. What's the volume between the 2 plates?
Air times T.
Yeah, it's like a box of area A, and then height D. So it's like, what's the area of this, or the volume of this room? If I know the area of the ceiling, I can multiply it by the height, and that's my volume. So area times D. So A times D. Now, if I have a parallel plate capacitor, so I have this, 1/2. The capacitance is epsilon naught times A over D, right? That's the capacitance of a parallel plate capacitor. How is the voltage related to the electric field? ED, yes. Voltage is the electric field times distance over AD. And you get this. You would have 1/2 epsilon naught. This area cancels with this area. 1 over D multiplies this 1 over D becomes D squared. And then here you will have E squared and then D squared, right? E squared, D squared. Those D's cancel. And so this U of E, little u of E would be 1/2 of epsilon naught times E squared. Okay, that's the energy density. Energy per unit of volume. So this was derived for the case of parallel plate capacitor, but it turns out to be general. It applies to any region where there is an electric field. So that is the energy density. Okay?
Professor,
Yeah.
what would be the units?
Joules per cubic meter.
Okay.
Yeah. Yeah. Good. So this one is joules per cubic meter. Now, capacitors, another thing that you can do is you usually want to increase the capacitance to hold more charge for a given voltage. So the way to do that is, you can make the area incredibly big, but you can't just make it arbitrarily big. You're limited by space, right? You're constructing components in your, let's say, flashlight camera or cell phone. They can't just be big, right? You want a small device. You can make the plates really, really close to each other. And then also that there is a limit to how close you can get them. And so people put a dielectric between them, which is an insulating material. And that insulating material turns out to increase the capacitance. So we want to see why it increases the capacitance, all right? So I would need these two boards now. Can I erase them? The left one? Yeah, you can. So that's the next step. We're going to put a dielectric and see what happens. How that works. So just remember, a dielectric is a conductor or an insulator? An insulator, good. Because you're going to put it between the plates. If it's a conductor, you're going to discharge them. If the two plates are connected by a conductor, the charge will have a path to flow from the plus to minus, and you just discharge it. You're going to put an insulator. Okay? And can I go on and erase? Yeah.
Yes, increase capacitance.
And here's how it looks like. I'll just give you an idea. I will leave that side, this one. So here is my capacitor. Here is the capacitor. Okay. Here's plus. Here's minus. And what you do is you come in and put a dielectric between the plates. So here's plus. Here's minus, and now you put a dielectric some kind of a material between the plates. That's the dielectric. That's the material. So the plates look like this, right? The electric field between them is this way, isn't it? So what does an electric field in this direction do to pluses and minuses here? Yeah, the pluses will be pushed away, right? So the pluses, if you have an electric field in this direction, or you can think of these pluses, they don't want the pluses within this material that you placed. So they want to push them to the left. So they will polarize that material. The end effect is this. You'll have some pluses this way from the material and some minuses, okay? Now what do they do? When you have this set up from the material itself that you placed, you have pluses on this side now and minuses on this side, what do? They produce their own electric field this way, right? And that electric field will partially cancel your electric field that you started with. And usually they cancel it by a certain fraction. Okay? So the new electric field now, after your field has been canceled, the new electric field, let's call it E, and the electric field here, let's call it E0. This new electric field, E prime, or just E, will be E0, whatever the electric field used to be, but less. It will be slightly less. It will be divided by a certain amount. And that certain amount is called kappa, or the dielectric constant. So it will be divided by a certain amount. It's like a K, but it has a little thing here called kappa. So this thing here, kappa, is the dielectric constant of the material that you have placed. In vacuum, it will be nothing, right? It will be divided by 1, because it will not change. So 1 for vacuum is just 1. For air, as you may expect, it's almost 1. So there's a table in the book. For air, it's like 1.0006. It's 1. And there are other materials, okay? So they can be as many as, let's say, paper would be about 4. Water is about 80. And so on. You get a few hundred, even a few thousand. Okay? So what does this do then? If the electric field is less, then what is the voltage? Remember what the relationship between voltage and electric field? If the distance, yeah, ED, yeah, the distance is D, so it's E times D, and so that's equal to, E is E0 over kappa, so it's E0 over kappa times D, right? Times D. But E0 times D is the original voltage, right? It's V0 without the dielectric. E0 times D is V0. So V0 over kappa. Okay. By the way, kappa is what units? What should the units be, if any? No, yeah. You got E on the left, E on the right. This quantity should be dimensionless because you have to have the same units. Now when you put the dielectric, the charge on the plates of the capacitor, does it change or does it stay constant? Charge on the plates. It stays constant, yeah. It's an insulator. It does not let charges flow from plus to minus or minus to plus. An insulator. So the total charge is still the same. So that means the capacitance, this new capacitance, will equal to the charge, it's just the old charge, divided by V, and so that's equal to Q over, but V is V0 over kappa, so that's kappa times Q over V0. But Q over V0 is the original capacitance, is the capacitance without the dielectric. So that means that the new capacitance, when you put a dielectric on, it's kappa times the old capacitance, the capacitance without the dielectric. So when you put a dielectric, it increases the capacitance by a certain kappa, by a kappa. So let's say if you put water in there, which has, I think, a dielectric constant of 80, then the new capacitance will be 80 times what it used to be without the dielectric. Okay. Pure water, so it's not a conductor. Okay? Alright. So that's what a dielectric does, it increases capacitance. Yeah?
Just to check, is that is supposed to be the right side? No, in that the graph drawing you did?
Sure.
Just like, yeah, E.
Here?
No, the down.
You should be pointing at the right.
Not to the left. It's still the same electric field in the same direction, but decreased by a certain factor.
Oh, that E net.
Oh, I see. This is the total electric field. After the effect of these has cancelled this one partially, this is what remains. So yeah, technically this little vector is a result of this bigger vector minus the this little vector that these produce. So that's the net effect. So again, the idea is dielectrics, basically what do? They increase our capacity. That's what. One. How much time? Okay, I have a calculation that I wanted to do, which is finding the capacitance for something that is not a parallel plate capacitor. So what if I have a setup that is not a parallel plate capacitor? How do I find the capacitance? So if you have another geometry, parallel plates, okay, we got it. It's epsilon naught A over D. What if I have a cylindrical capacitor? A cylinder. So let's say I have a cylinder here of, let's call it radius R1, and it has plus charge, and it's, so it's lambda, positive lambda. The charge per unit of length is lambda. All right? And now, we encountered this problem before when we did Gauss's law. Let's say I have another one that is a negative charge here, a negatively charged. This cylinder is negatively charged, and it has minus lambda on it. The charge per unit of length is minus lambda. The question is, what's the capacitance between them? We say capacitance per unit of length. Let's say the cylinder is long, infinitely long. Okay. So, and this outer cylinder will have a radius R2. Yeah. So what's the capacitance? I need to do this. I need to figure out what the change in potential from here to here is, and then divide by the total charge, or do Q over V, and then see what I get, right? By definition, remember, by definition, capacitance is Q over V. Okay? Q over V. So what's the potential difference between the plus and the minus? So, we are not in the chapter of Gauss's law, but it doesn't mean Gauss's law is no longer applicable. It's still there. Yeah. So, by symmetry, what kind of surface would you choose?
A cylinder.
A cylinder, the Gaussian surface. So Gaussian surface of radius, let's say R, and length, let's say L, right?
Yeah.
Length L. Yeah. So we know that E dot dA, right? E dot dA over a closed surface will equal to Q enclosed over epsilon naught, isn't it? Now, the idea of choosing a Gaussian surface that's cylindrical so that E dot dA just becomes E times dA, and on the curvy side, on the ends it's zero, right? Dot product is zero because they're perpendicular. So you just have E times dA, and so you would have E times dA, and then over the curvy side of the cylinder. And then here, what is the charge enclosed? Well, the charge per unit of length is lambda, so the charge enclosed will be lambda times L, times the length of my surface. So lambda times L divided by epsilon naught. Now the E field is constant as long as I'm at the same radius, so E comes out. And what is the area this way? If the length is L and the radius is R?
2 pi r L.
2 pi R L. So E 2 pi R L equals lambda L over epsilon naught. L cancels and you get the electric field will be lambda over 2 pi epsilon naught R, right? That's the electric field. The direction of the electric field, if this is the plus, then it will point outside, radially outward, right? Radially outward. Now, let's find the potential difference between the two plates. Right? By definition, what is the change in potential? Delta V is what? The integral of what? E dot dr. E dot dr. And is that it, or there's a little pesky minus sign?
Oh, yeah.
Yeah. There's that little minus sign. So, and I'm integrating from R1 to R2, right? I want to find the potential difference from this cylinder to this one. Between the two cylinders. So that's that. And so E and dr are parallel to each other. Both are in the radial direction. So when you take the dot product, it just becomes E times dr. So this becomes minus the integral from R1 to R2. But E is lambda over 2 pi epsilon naught R. So lambda over 2 pi epsilon naught R is in the bottom, and then dr. Alright? Now lambda, 2 pi epsilon naught are all a constant. And so you're integrating 1 over R, which is natural log of R, right? R is positive. So you have delta V is minus lambda 2 pi epsilon naught natural log of what? R2 minus the natural log of R1. So it becomes R2 over R1, right? Difference between natural logs will be the quotient of their arguments. Okay. So now, the capacitance. What's capacitance? Capacitance is the change in, oh, by the way, since R2 over R1, R2 is larger than R1, this is a positive quantity, right? This is more than 1, so that's a positive quantity. And the potential change is negative, and that makes sense. Yeah.
Is the second cylinder, is that a hollow one?
The second, this one?
Yeah.
Yes.
Okay.
Yeah, it is hollow, yes. I should have probably emphasized it. Yeah. Now, otherwise, we would have to do it differently, right?
Yeah.
We'll have that volume element. Does it make sense that we have a minus sign? Yeah.
Can you expand a little bit as to why the change in the potential is
Negative?
negative?
Yeah, so that's my